Hi, so in this video we are going to discuss how to interpret coefficients correctly, how the scale of variables affects the value of coefficient, and how to design different functional forms of regression models depending on theory assumptions and other circumstances. So let's start with coefficients. Here you can see some regression output. In this model, we assume that GDP growth in period t is affected by the level of GDP in period t minus 1. It's easy to notice that this model was designed based on time series dataset because you have coefficient t, you have index t. In case of cross-sectional dataset, this index would be I, and in case of panel data, this index would be Ti, because again, in cross-sectional datasets, you assume that there are several agents observed for one period, and in case of panel dataset, you have several entities, items, whatever, observed for several periods. But in this case, we have just one country observed for several periods. So as you remember, we express beta 1 units of measurement instead of the ratio of units of dependent variable to units of explanatory variable. So speaking very informally, beta 1 can be interpreted as how many units of dependent variable per one unit of explanatory variable. So in our case, beta 1 is equal to 0.11, and first we assume that GDP is expressed in billions of US dollars. So based on the obtained value of beta 1, we can conclude that if GDP in period t minus 1 increases by 1 billion of US dollars, then GDP growth in period t will increase by 0.11 percentage points. And I would like to emphasize that it will be exactly percentage points, not percent. Because obviously GDP growth is expressed in terms of percentage points. Like usually it's from, I don't know, -2 to +5%, something like this. But the difference, in your interpretation would be dramatical, depending on whether you mention percentage points or percent. I believe it will be more intuitive if we discussed it based on the sum example. So assume that in period 1, unemployment rate is equal to 20%, and in period 2, unemployment rate is equal to 30%. So in this case, unemployment rate increased by 50%. Basically, if you multiply 20 percentage points by 1.5, you will get 30 percentage points. But at the same time, it increased by only 10 percentage points. So I believe it's kind of intuitive and you can easily notice this difference. So please be very, very careful when you interpret coefficients in the regression model, especially when you use variables expressed in percentage points, like GDP growth rate, unemployment rate, inflation rate, poverty rate, and so on and so forth. Okay, so now let's proceed to the scaling. As you remember, previously we expressed GDP in terms of billions of US dollars. Now we can see what will happen if you express GDP in millions of US dollars. So as you remember, beta 1 is all about the ratio of units of the dependent variable by units of independent variables. So saying dividing percentage points by billions of US dollars is equivalent to dividing percentage points by the product of millions of US dollars and 1,000, because 1 billion is 1,000 greater than 1 million. And as you remember, this coefficient was equal to 0.11. So if you want to express independent variable not in billions but in millions, it will be equivalent to dividing coefficient beta 1 by 1000. Again, you can easily detect it from this formula. So in this case, instead of 0.11, beta 1 will be equal to 0.00011. Of course, it does not change anything in terms of the functional relationship between GDP in period t minus 1 and GDP growth in period t. What I mean is that stating that if GDP in period t minus 1 increases by 1 billion of US dollars, then GDP growth in period t will increase by 0.11 percentage points. And if GDP in period t minus 1 increases by 1 million of US dollars, then GDP growth in period t will increase by 0.00011 percentage points. It's the same. So two statements are basically identical, although the first one is definitely, how to say it, friendlier to the reader when it comes to the regression output. So this might be the problem. If you download data from the World Bank, let's say data on GDP, all the values will be expressed in terms of US dollars. And you will get some ridiculously small value of beta 1 coefficient. So that's why actually it makes sense to express big values, not in original units, but let's say in billions and millions, just to simplify the life of the reader, because analyzing this number is definitely easier than in case of this one. So basically it does not change anything, it just makes your regression output look more professional. So please take this into account when designing a regression model for your coursework. So now we proceed to the second part, which is all about functional forms of regression models. So far we analyzed linear model in terms of both in terms of coefficients and in terms of variables. Now we are going to proceed to the models which are linear in terms of coefficients but not linear in terms of variables. And we will start with log-linear model. So before we proceed to the log-linear model, I would like to recall the notion of elasticity. And basically elasticity is the measure of responsiveness of the value of dependent variable to the change in independent variable. And this measure will not depend on the original units in which these variables are expressed. So this change will be expressed in terms of percentage change. So as you remember, you calculate elasticity as the ratio of marginal function and average function. And what I want to say is that in log-linear model, which is presented here, beta 1 will be interpreted as elasticity of y with respect to x. So beta 1 will be identical to what you can see in this formula. So this is the idea. In this case, we will not use the original units in which the variables are expressed. Instead, everything will be presented in terms of percentage change. So again, please be very careful with this when you interpret regression output, especially when you use log-linear model. Okay. So here it is. As I said, in this case, both dependent and independent variables are presented in the form of natural logarithms. So basically, you have to take the natural log of both sides. So let's say if beta 1 is equal to 5, then increase in the value of x by 1% will result in 5% increase in y. Please pay attention to the fact that I said percent, not percentage point. So log-linear models can be extremely useful when you analyze theoretical multiplicative models. So for instance, here you can see gravity equation of international trade, We already discussed it when we analyzed dummy variables. So according to this model, the volume of international trade between countries I and J can be expressed as the product of A, which is constant, and the ratio of product of GDPs of these countries taken to the power of beta 1 to the value of geographical distance between those two countries taken to the power of beta 2. Looks kind of complicated. But then you can just take the natural log of both sides using this kind of simple rules, and you will get this. So now beta 0 will stand for this constant, constant in the original theoretical model. Beta 1 will serve as the coefficient of the natural log of the product of GDPs, and beta 2 will stand for the coefficient of the natural log of distance. And of course we have to add error term because no regression model is perfect. So if you're good at math, you could say that here we actually should have minus, because you divide by distance. So actually, yeah, you have it here. But actually it doesn't really matter. So you can just have distance expressed in its original form, like 800 kilometers or 1000 miles, whatever you prefer. And then the regression coefficients will be defined by the regression model output. So what I mean is that if your model is specified correctly, you should get negative coefficient of distance. Because if you take positive coefficient of distance, it will imply that geographical distance between two countries affects the volume of trade between them positively. So this is ridiculous. This contradicts economic theory and common sense, and it would mean that you misspecified the model. But nevertheless, you do not have to make any special operations, when designing this regression model. So, of course, you should have negative coefficient in front of the distance variable, log of the distance variable, but this is not your task. It will be specified by the regression model, or misspecified, as I mentioned before. So, if the product of trading partners' GDPs in period T increases by 1%, then the volume of trade between countries I and J in period T will change by beta 1%. Analogously, if the distance between trading partners increases by 1%, then the volume of trade between them will change by beta 2%. If beta 2 is negative, then it will decrease, but I believe you've got this idea. You do not have to, do any additional transformations when it comes to the distance variable. It will be just defined by the regression model output. So when it comes to natural logs, okay, give me a second, it's not visible to you. So you can use Gretel in order to transform the variable to the natural log of this variable. So, okay, I will show you something. So let us take GDP growth, add logs of selected variables, close. So here you have it. This is the natural log of GDP growth. However, the problem here is that now I completely omitted all the negative values of all the observations with negative values of GDP growth. Because obviously you cannot take the natural log out of the negative value, but GDP growth can be negative, in the period of economic recession. So that's why, log linear model is not really applicable when you deal with variables which take both positive and negative value. Please be very careful about this. So, there is nothing which would prevent you from doing so. It's just not right. So, you artificially narrow your sample by completely excluding all the observations where the values of your variable are negative. But for instance, I can do this with natural resources rent, which is the percent of natural resources rent out of GDP. So again, not log difference. Oh, sorry. Add log of selected variable. Yeah. So here I also have missing values, but not because of negative values, but because there are some gaps in my data. So now it's fine. Just make sure that you do not do natural log transformation with variables which take some negative values. So here you can see some visualization. So usually market demand curve is defined by the convex function. I mean relationship between price and quantity demanded. And you can see this formula here, which is again a kind of exponential, not exponential, but let's say multiplicative model. But if you take natural logs of both sides, it will just give you a nice linear model with a negative slope. So again, it will just simplify your life a lot when estimating this. But again, I would like to underline that, for instance, in case of Phillips curve, it will not be the best solution because inflation can take negative values in the periods of deflation, and if you take the natural log, you will just drop all the observations with negative inflation. So this is something which you are not allowed to do if you'd like to estimate a nice and unbiased model. Okay, so another thing is log-LIN model, and as the name suggests, in this model you take natural log of the dependent variable, and independent variable remains a linear term. So in this case, you interpret beta 1 as the percentage or relative change in the dependent variable accompanying absolute change in the independent variable. So let's assume that beta 1 is equal to 5. So this means that if x increases by 1 unit of x, so let's say if x stands for GDP expressed in billions, if x increases by 1 billion and if beta 1 is equal to 5, then y, like dependent variable, will increase by 5%. So again, now you express change in the dependent variable as the relative change, and you express change in the independent variable as the absolute change. Okay, in LIN-LOG model, just the opposite. You take the natural log of the independent variable, and the dependent variable remains expressed as a linear term, and then beta 1 is interpreted as the absolute change in the dependent variable accompanying relative change in the independent variable. So let's say beta 1 is equal to 5. Then, if beta 1 is equal to 5, increase in x by 1% will result in 5 unit increase in y. And vice versa, decrease in x by 1%, by decreasing x by 1%, you will decrease y by 5 units. Again, if we assume that beta 1 is equal to 5. Okay, finally we proceed to reciprocal model, and in this case you have to take the reciprocal value of the independent variable. But again, please keep in mind that the signs of the regression coefficients will be defined by the regression model output. So for instance, if we assume that beta 1 is greater than 0, then the regression line will look in this case. So it will approach the value of beta 0, but it will never reach it, and vice versa. Like here we have the opposite. If beta 1 is negative, then we have increasing concave function, And in this case, again, the value of the dependent variable will approach the value of beta 0, but it will never reach it. Okay, so these models are kind of appropriate for estimating well-behaving convex and concave functions. So for instance, you can detect that this one looks very similar to Phillips curve, for instance. So yeah, you can easily put inflation here, unemployment here, and this will be the relationship between inflation and unemployment as predicted by economic theory. So basically, this kind of model will be appropriate for estimating Phillips curve, let's say. Or, any function of the similar shape. I just cannot come up with a good example at this point. Okay, finally you have logarithmic reciprocal model, which has this weird shape, and in this case you have to take the log of the dependent variable and the reciprocal value of the independent variable. So you can notice that this function has some nice property. Up to some point it's convex, so this function is increasing with increasing rate. Like speaking less formally, this function will grow faster as the value of x increases, and from this point the function is concave. So here we have decreasing rate of increase, let's say it in this way. So actually this function is typical short-run production function. So we assume that if the level of input is relatively small, then we deal with increasing returns to scale, and when it increases, we deal with decreasing returns to scale. So this is kind of it. If you can kind of come up with any, other piece of economic theory which would be relevant for this shape of function, please feel free. Again, I just cannot come up with any other example at this moment. Maybe later. So in all the regression models we discussed so far, the effect of the independent variable on the dependent variable was uniform in terms of direction. I will explain. So as you can see at this graph, increase in input will be always accompanied by increase in output. Of course, after some critical level of production is achieved, each additional unit of input will be less and less helpful. I mean, the marginal productivity of each additional unit will be smaller and smaller, but nevertheless, increase in input will be always accompanied by increase in output. There is no way to decrease output by increasing input. So this contradicts the common sense and logarithmic reciprocal model as well. Analogously, like what you can see at this graph, increase in the level of x will be always accompanied by increase of y. For instance, if you analyze the relationship between inflation and unemployment, there will be always negative relationship. So unemployment increases, inflation decreases, and vice versa. Unemployment decreases and inflation increases. Okay, you've got the idea, I believe. So there is no way to see increase in unemployment and increase in inflation simultaneously, at least, under the framework of conventional macroeconomic modeling. But I believe you've got the idea. However, sometimes the effect the independent variable causes on the dependent variable would depend on the relative value of the independent variable. Okay, probably I should explain this based on some example. So for instance, you know that young employees have lower income in comparison to middle-aged employees. At the same time, middle-aged employees have higher income in comparison to elder employees. So as you can see, wage increases your income, but only up to some point. Let's say this point is 45 or 50 years. Or we can discuss it based on Kuznets curve. So the moderate level of income inequality causes positive effect on economic growth. So economic growth increases with income inequality. However, if there is too much inequality, increase in inequality will be accompanied by decrease in the rate of economic growth. So I believe you see this idea. So in this case, if you analyze any economic problem and the logic I described here is relevant to your analysis, then you can add the square term of x to the regression model, like here. Of course, there might be different signs of beta 1 and beta 2 coefficients depending, on the character of this relationship. So here we can see some examples. So for instance, if beta 1 and beta 2 are both negative, so coefficients of the linear and square term are negative, then you have this inverted U-shaped, like Kuznets curve, for instance. If beta 2, the coefficient of the square term, is positive and beta 1 is negative, then it will look in this way, and so on and so forth. So you can see different combinations. I would say that those two are the most common, but of course everything will depend on, the setting, like the model setting, the range of values of the dependent and independent variables, and so on and so forth. But nevertheless, this is what you can do if you analyze some economic problem and again you suspect that the effect of x on y is not uniform in terms of direction of this effect. Because again, as you can see here, up to some level of income inequality, increase in income inequality is accompanied by increase in economic growth. After some level is achieved, then increase in income inequality will be accompanied by decrease in the rate of economic growth. Or the same here, until you reach 45 years, your income will increase with your age, but after this point, your income will decrease as your age increases. So something like this, I believe this is pretty intuitive. Okay, so just to make some conclusion, how you choose the functional form of your regression model. First of all, you should check the theory. So if you analyze the relationship between inflation and unemployment, then you have some nice piece of macroeconomic theory which tells you that this trade-off is described by Phillips curve, and Phillips curve is the convex decreasing function, as simple as it is. If you describe the relationship between inequality and GDP growth, then again you can easily check Kuznets curve, who designed some explicit theory explaining why this function should look in this way. So, and so on and so forth. I believe you've got this idea. You can check out the elasticity at the different levels of variables to see, on the different values of the independent variable to see whether it's uniform, because if it's uniform, then constant elasticity model is the model of your choice. Or you can simply do some raw data analysis, like, just checking some observations. So for instance, I believe I demonstrated this before, but in case you would be interested, like if I want to check the relationship between income inequality described by Gini coefficient and let's say the level of income per capita, then of course you can design some linear trend based on this, but linear trend is definitely not the best representation, So at least to me it looks kind of inverted U-shaped curve, but maybe you have to have some imagination in order to see this. But nevertheless, like, this is the idea. So you can simply check, the observations, do some plot analysis. In Gretel, it's also an opportunity to check whether linear specification of the variable was indeed the most suitable. So in this case, you have to run a linear regression model specifying, again, according to what I mentioned, GDP per capita as dependent variable and Gini as the regressor. Here you have it. So of course I have only one variable, that's why everything is pretty statistically significant. So this test, you see, nonlinearity squares. So let's do this. And yeah, actually tells me that adding the square term of Gini coefficient was a good idea. It's still statistically significant, and my test statistics shows me that it was indeed a good idea. Okay, but this is some optional, I just show it to you in case you're curious about this stuff. Okay, so finally your home assignment for the next week. As usual, please submit by Saturday. So your task is to design a nonlinear in terms of variables model. You have to explain very briefly the choice of the regression model functional form. So basically something I discussed here, if you suspect that the direction of the effect X causes on Y is not uniform. If you have some economic theory which suggests that the function should be convex or concave or whatever, or if you deal with a multiplicative model. So again, it should not be very long, just some very basic explanation, maybe half a page or even less. And finally, you will have to present the model output and interpret the coefficients. I have a minor request, so please submit everything in Word form. You can just take the print screen of the model output and insert it to the Word document. Again, this is not obligatory, this is just my kind request. It will simplify my life a bit. And yeah, that's it. So thank you for watching, and I will look forward to receive your homework.